In this video, we're going to discuss when a vector field defined in the plane is conservative. To get started, let's suppose that you've given me a vector field f, and we're working in the two-dimensional plane, so I'm going to have two components. There'll be m and n, and there'll be functions of x and y that determine the I and the j component, respectively. Let's suppose for the time being that my field actually is conservative. So let's suppose f is conservative on some, of course we have to say where, on some region r in the plane. To be conservative means that there is a potential function which we've been calling phi, whose gradient field is in fact f. So let's suppose f is conservative, and we can write f is equal to the gradient of this function phi. To compute the gradient, you take the partial derivatives of phi. So the first component will be d phi dx and d phi dy. Comparing the components, if this is really a true equation, it must be that my m is d phi dx, the first partial derivative with respect to x. And that n, the other component, the j component, is d phi dy. I'm going to take m and I'm going to differentiate that with respect to the other variable. In this case, I was already differentiating with respect to x, so I'm going to take the derivative with respect to y. That expression there is now a mixed second-order partial derivative of the potential function phi. It is the derivative of phi first with respect to x and now with respect to y. Similarly, I'm going to take the derivative of n with respect to x. This is also a mixed second-order partial derivative, first with respect to y and now with respect to x. And under reasonable conditions, if these functions m and n, or phi rather, is nice and continuous in its derivatives, has nice second-order derivatives, and they are in fact continuous, then it turns out that a famous theorem says that these second-order mixed partial derivatives must agree. So right here we have a condition on the components of my field m and n that have nothing to do with phi, this potential function, that we can check. And if my field is conservative, it must be that dm dy and dn dx are in fact the same. I'm going to write this in a slightly different way. I'm going to subtract, and I'm going to put dn dx on the left and dm dy on the right. And the equivalent statement here is that their difference is in fact 0. So if this field is conservative, this quantity of partial derivatives should be equal to 0. This quantity on the left has a name, and we're going to make a little definition here. This quantity is called the curl of the vector field. So the curl of f, we'll write it this way, is the partial derivative with respect to x of the j component of your field, and the partial derivative with respect to y of the I component of your field. And our conclusion right now is that if my field f is conservative, then the curl of that field should be 0 on the region that we're talking about. Loosely speaking, conservative fields are curl-free. They have no curl at any point on the region where they are conservative. So our condition right now is if f is conservative on a region, then it is curl-free on that region. Let's look at two examples. I'm going to take the vector field x and y for the components, and let's compute its curl. M is equal to x, n is equal to y in this case. I take the partial derivative with respect to y of m and the partial derivative with respect to x of n. And because I've got this mixture of variables here, y, but of x, I'll get 0. And similarly y, but with respect to x, I get 0 here for the partial derivatives. So if I compute that curl, the curl is the difference of the two, and I get 0. This vector field is curl-free. And in fact, it's not a shock that this thing is conservative, because if I have x and y in each of those components, I feel like I should just have x squared over 2 and y squared over 2 as terms in some potential function. So if I take this function here, x squared over 2, and I differentiate it with respect to x, I indeed get my x, and if I differentiate this other term with respect to y, I indeed get my y. So my field is in fact the gradient of this quadratic expression, and therefore f is conservative, in fact on the entire real plane. If you look at a picture of this vector field, you'll see that it's very expansionary in nature. It's all expanding from the origin. As you move further away from the origin, the vectors get longer, and the vectors are all pointing away from the origin. It turns out that curl is some sort of measurement of rotation at a very local level of the field. And that's very vague what I'm saying right now. But because this vector field is curl-free, it's an indication that this vector field only has expansion or contraction at a local level. And in fact, it's the gradient of this, and the gradient is kind of telling you which direction you should be going to in order to see the value of this function increase. In this case, you need to move away from the origin to see this quadratic expression increase most rapidly. Let's look at a complementary example here. I'm going to take minus y and x for my components. So m is minus y, n is equal to x. We take the partial derivatives. And in this case, I get minus 1, and I get 1 now. And the way that I've swapped the order of the variables ensured that I got non-zero derivatives. And I look at this thing called curl, and I take the derivative with respect to x of n, and then this partial derivative here, I have 1 minus negative 1, which gives me 2. All right, well, this is non-zero anywhere. This function is not conservative as a result. Anywhere in the plane, there is no potential function whose gradient is equal to this field. If there was, I should have gotten 0 for the curl, but I got non-zero for the curl, and therefore it just cannot be conservative. If you look at a picture of this vector field, you'll see that there's lots of rotations. There's lots of swirling around and rapidly moving around as we move further and further away from the origin. And again, curl is some sort of, and I keep qualifying this by saying local, curl is some sort of local measurement of rotation or swirling of the vector field. We'll make that more precise later on. But this one's clearly got some rotation as I go around, and therefore it doesn't look like it's going to be conservative.